Hello, I'm Kaden Korn, and this is my Physics 2211 Lab 5. I chose to focus on the motion of a basketball for this lab. So first of all, I'm going to introduce this. The purpose of this lab was to analyze the motion of a basketball shot and then compare that motion to the motion predicted by a computational model. Now, this computational model will be a Python program in GlowScript, the same one we've used all year, that'll be used to predict the motion of the ball. So first of all, there's a few necessary physics principles to complete this lab and to understand it. These are the velocity equation, position equation, average velocity equation, which you can see here. F net equals ma, as well as derivations of this equation used for others. And then finally we have the fully updated position formula that takes into account pretty much all factors. So now for the method. First of all, I had to actually go online and find a video of a man shooting a basketball from the free throw line, which is, according to Tracker and according to my research, about 5.8 meters away. Then I analyzed this motion in Tracker. I observed this motion. I recorded it, and then I visualized it, and then I compared the predicted motion from the computational model to the observed data. And you'll see what these actual results were in a minute. There were some conditions that should be defined to make the lab clear. First of all, the system was the basketball. The surroundings was the earth, because that's, gravity is the only thing really acting on it here, to our knowledge. Initial velocity is 7.4 meters per second, and the initial position is negative 0.02 in the x, 2.337 in the y, and no z. It also should be said that there likely is a z here, but we're limiting this motion to be purely two-dimensional since most of it is in the x and y planes. So here's a preview of a couple of the important lines of the code. First of all, in this top left box, there's just some initial conditions, such as gravity and mass and all these other ones you see. They're defined to the right if you want to read those. And then down here is more initial conditions, as well as setting up these vectors for the initial position and velocity. Or sorry, for the actual position and velocity as variables. Then over here you have the kinematic calculations. So these show the position of the apex, shown by y top and x top, as well as more calculations that'll become useful in other areas of the code. And then finally in this bottom right section, you have the actual position adjustment loop, which is seen in this while loop. You can see there's total time and delta t initially defined, and t is initially set equal to 0, so that this loop will keep increasing until it reaches its total time, and this velocity and position will be updated every single time so that it's correct. And it does this all the way until time equals 3. So now it's time that we discuss some of the findings here. So first of all, as you can see, the predicted motion looks very similarly to the shot in the video. And what this means is that the paths that both of these followed were pretty similar. This means that the observed and computational models were relatively similar, meaning that the computational model was relatively effective. Also, I noticed that the observed trajectory peak was actually higher than the model, which I thought was a little weird, because I figured if any apex would be higher, it would be the computational model, because there's no drag. So that surprised me a little bit, but that means that it's likely due to one of these other potential errors, such as converting the real time with Tracker to make sure that the times really match up. Or this is likely the biggest one, is the angle of release estimation. Since you're shooting a big basketball and there's camera angles and things like that, the theta was probably off originally by chance. And then any extra forces that may be there. So now it's time for an additional question. I created a question here like at the end of all these labs, and that's what if the shot was shot from much further back? For example, a full court shot or something like that. Well, obviously it's intuition that you would have to throw the ball harder, and this means that initial velocity would be higher. It also may be in your human instinct to throw this ball higher, and where this comes from is that what this means really is that the combination of initial velocity and launch angle decides how far the ball will travel. And in your brain, your tendency to throw something far is to throw it as hard as possible and try to throw it at about 45 degrees or a little bit lower, which makes sense with this data. And that's what would change if we change the distance. And thank you so much for listening.